For my application of linear algebra, I decided to talk about PageRank and how it relates to eigenvectors. So PageRank just represents the importance of a web page. The higher the PageRank, the more important the page is, and it aids in determining which pages to show for a search. Since when someone wants to search for something, they probably only want to see the good web pages, the ones that are deemed important, not the ones that are, bad sources or just not interesting. So this algorithm was developed by Larry Page and Sergey Brin in 1996 for Google, as they were making Google at the time. And this really helped Google become quite powerful as a search engine. It made it very effective and very good at displaying results that people would want to see. So how do we find the PageRank? Well, to do that, we're going to let the PageRank be I of pi, so the PageRank of some page, pi, is going to equal this sum. And what is this sum? So essentially, this is just we're going to look at only sites that link to our site, and we're going to say the PageRank of that site, we're going to divide it by the number of other sites it links to. So basically, PageRank is simply just looking at other sites and how many times that this one particular site that we want to find the PageRank of gets linked by these other sites. But we want to make sure that we don't consider a site that links hundreds of pages too importantly. Because if they're going to link 100 pages, then any given link probably isn't as important as a site that only links 2 pages, for example. So that's why we're dividing by the number of pages of J. And so, but this formula seems to require us to already know the PageRank of other sites, and that's a bit of a problem. Since we don't know the PageRank of those other sites, we're trying to figure out the PageRanks. So what do we do then? Well, we can think about this from a different perspective. Suppose we create a matrix H, which is going to be our hyperlink matrix, and in the ijth position, we're going to have 1 over Lj if Pj links to Pi. All we're saying is we have some site Pj, and it's linking to the site that we're trying to find the PageRank of, and we're just going to divide it by the number of pages it links to. And if it doesn't link to the site, then we're just going to put 0. And we're also going to define this vector here. And all this vector is just the vector of PageRanks contains all the PageRanks. And that's all this vector is doing. So thinking about this, we could rewrite this formula up here a little bit differently. We could think about it this way instead. We're going to multiply by the PageRank of page J. We're going to multiply that by the hyperlink matrix. And we're going to do this for every single other page that's linking to our site that we're trying to find the PageRank of. And if we really think about it, this is just the same as saying we're going to multiply the hyperlink matrix by this matrix, the matrix containing all of the PageRanks. And we want it to equal the PageRank because, well, that's the goal. We're trying to find the PageRank of these sites. And this is suspiciously similar to this equation right here. In fact, if we set lambda to 1, it's the exact same equation. This PageRank vector is actually an eigenvector. In fact, it is the eigenvector of H that has eigenvalue 1. Now, that might have been a little bit confusing. I think we should go through an example to better understand what's happening and what PageRank is. So let's imagine we have a web, and the web contains a total of 5 web pages. And then each column here is just representing what sites that the page here, so page 1, what sites is it linking to? And we can see that page 1 is linking to site 2, page 3, page 4, page 5, and then we'll take a look at page 2, and we see that it only links to one page, page 3. And we have page 3, and it links to pages 1, 2, and 4. We have page 4, it links to page 1 and page 5 links to page 1 and page 2. Now, notice that no site links to itself. That's very important. If it does link to itself, it would start causing problems, and this does not work at all in the way we would want it to work. So we want to transform this into a matrix, because as a table, it's not very helpful. And so we have this matrix over here. And we can see that, well, since page 1 doesn't link to itself, we put a 0. But it did link to page 2, page 3, and page 4, and page 5. Since it linked to a total of 4 pages, we're going to divide by 4 for each of these. We're going to have 1/4, 1/4, 1/4, 1/4. And page 2 links only to 1 page. So we're going to have 1 divided by 1, which is just 1. Page 3 linked to 3 pages, so for each one of those pages, we have 1/3 instead. Page 4 linked to 2 pages, so 1/2. And page 5 also linked to 2 pages, so those are 1/2. Now you might notice that every column adds to 1. That's a little bit of an interesting thing about this matrix, and also part of why this does work is the fact that it is adding to 1. In fact, because of this, we know that our page ranks will be positive. In fact, if they weren't positive, that'd be kind of bad, because what would a negative page rank even mean? So thankfully, because of the nature of this kind of matrix, we will get a positive result, and it will make sense. Alright, so now we need to solve for the eigenvector with eigenvalue 1 of the hyperlink matrix, because, as we can recall, we are looking at eigenvalues and vectors. Because remember, the page rank is an eigenvector. So, to do this, as we can remember from our course, is all we have to do is take the eigenvalue and subtract it off from the main diagonal of our matrix, which just means that the main diagonal is now -1, -1, -1, -1, -1, and nothing else has changed. And then from there, we just have to find the reduced row echelon form of this matrix, because recall eigenvector, to find eigenvector, we're finding the basis of the kernel of this matrix. And so the reduced row echelon form of the matrix is just this one right here, which then gives us these equations. We can see that x1 equals 7/4 x5, x2 equals 13/8 x5, x3 equals 33/16 x5, x4 equals 9/8 x5, and 0 equals 0 because, well, this row is just zeros. And then, using this, we can just see, we just plug that in to a vector. So we have 7/4 for page 1, 13/8 for page 2, page 3 is 33/16, page 4 is 9/8, and page 5 is 1 because we decided we're going to let x5 equal 1. And this is just what it is when we put it in decimals, because it's a little easier to know what's bigger when we see it in decimal form. And we can see then that, well, page 3 must be the most important page, as it has the highest page rank. And suppose we were using PageRank solely to determine how we want to display results, we would probably go with page 3 being displayed first. Then we would display, page 2 under it, then page 1, page 2, under page 1, and then page 4, and then page 5, because page 5 had the lowest page rank. It's the least important page in our little web here. So as we can see, using eigenvectors can actually be a very effective way of displaying search results. However, of course, it has limitations. In some cases, a page's page rank equals 0. And this is one of those instances. See, we can really imagine pages as just nodes on a graph, or particularly a directional graph. And what happened here is we can see that we have arrows pointing into this little subgraph here for nodes, but there's no arrows pointing out. And this just makes this entire little areas, or subgraph, have page rank of 0. And there is a way to address that, but that's kind of outside the scope of linear algebra. That deals more with graph theory and probability. Another problem is the web is just huge. I mean, there's billions of web pages. The matrix you would have to find the eigenvector of is huge. Again, there is a solution that Google had implemented, but also not really within the scope of linear algebra. And you also need other algorithms to work alongside it. I mean, PageRank is effective, but it's not perfect. Just because a site gets linked to a lot doesn't necessarily mean it's the best site in the world. Just because you have so many links doesn't mean everything. And surprisingly, Google actually does still use PageRank to some extent in determining which search results to show, but it's definitely not as prominent as it used to be, as machine learning has outpaced it in many ways. But nonetheless, PageRank is a very effective way of organizing search results. And, if you did have to organize a bunch of results for some reason, this would be a good way to do it. It's fairly easy to do, and I think that it's really quite nifty. That's all I have for this video, so I hope that I was able to convey the idea of PageRank effectively, and thank you for watching.